Okay. Let's go back to student preview, start preview. Okay, now we're back. We made it. It's Friday afternoon. We got a long weekend ahead of us. All right, first week is done. And then there's no breaks until basically the end of the semester. So soak it up, refresh, think about what your learning objectives are for the semester, what you want to get done, who you want to be. Last time I wanted to get to quiz 0, but we didn't have time for it. We had bigger things to figure out, like, do we even have free will? Like, did we choose to be here? Which, that's the big, important questions of life. So let's take a look at quiz 0 and kind of do this. It's also a nice review. Let's do this. Spectacle. Oh, do I have a screenshot? Maybe? Let's just copy it. All right, if you haven't figured out already, I like Spider-Man. So Spider-Man is swinging through the city. This is one of the classic first Spider-Man comic book covers. Maybe not the first, but it's a classic cover. And for this quiz, we're drawing a free body diagram of Spider-Man. So what is that? Actually, yeah. Why don't you try it? It only takes a second. I want to walk around, see what people are doing, and then I'll kind of take the composite view and put it up there, or maybe the different options. So try it out. Try to draw a free body diagram of Spider-Man. He's swinging. He's holding some kind of bad guy, or maybe his landlord. We don't know. We haven't really gotten any context yet. That's all right. Yeah. It doesn't. It can be as long as it has Spider-Man eyes. I'll make it. No, I'm joking. Stick figures are good. Yep.
What they call it? It's almost at its peak elevation in swing. It's almost perfectly horizontal.
Yeah. It could be 0 because it can be 0 tension,
But it can. I thought that was a whole force and then tension was going to get sleepy. He's swinging this way, right? He's moving to the left. He's got the weight of the bad guy. Oh, yeah. The weight is he's swinging that way. But that's a separate force. Because he's got a normal force to make sure he doesn't face me. I guess he's in the air. But he still has a normal force. The normal force is the tension. I guess. Yeah. I'm thinking of the elevator. I guess the force would be the so back to tension. Yeah. I mean, velocity is yeah, but I mean, that's like saying you don't generate any force because you're standing still. You do. The only force you generate is when I'm not accelerating upwards, the car is accelerating because there's no force. Chris, you're killing me. You're killing me, Chris. That's a problem. This reminds me of, what is it, P equals mg? It's probably 3. There's something conservation of momentum. So there's attention. And then there is a separate gravity. It's really you can consider I'm not including this rod is connected to like 10 the battery. I feel like this is always the first one. I actually like this side because this right now is the problem is that I don't know.
You know what?
It's a good room.
All right, so here's the first step. And I saw most people starting to do something like this, where you see the web, and webbing is like a cord. It's something like you can't like take a rope and push on someone with it. So the only thing you can do is like create tension with that. Great, good first thought. Then the other thing that almost everyone that I saw had like gravity is just, you can't do anything about gravity. It's always going straight down. You can go to space and now you have like different directions of gravity, but it's always pointed towards the biggest object. So straight down gravity. Now, and then from here we had some differing stuff. some people drew like the force of the bad guy, like the weight of, or yeah, some kind of connecting thing with the bad guy. So I saw different things. One was, I'm gonna call it MBG times G, like mass of the bad guy times gravity of the bad guy straight down. What did that do to the bad guy in my like assumed model of Spider-Man carrying this bad guy? Is it wrong? Did I do it wrong? Is it right? Is this the only way that you can do it? What do you think? Because I know I saw different things, so I want to know why you did it differently. Yeah.
Could you have the friction with that guy?
Some kind of friction between bad guy and Spider-Man? Okay.
The normal force the bad guy uses on Spider-Man there.
All right, so there's some kind of connecting force between bad guy and Spider-Man, right? That would be another way of doing it. There could be, you could say that Spider-Man's arm is creating tension. So and those two things that you're describing, those are constraint forces. Like the bad guy has to move with Spider-Man, otherwise bad guy is free falling through the air. Yeah.
Because you just saw it as like a combined mass of the both of them.
Yeah, so that's what I just did, is I just took both the masses and said, bad guy mass, Spider-Man mass, there is no difference. They're both one block of mass. But the other, if you're saying like, no, there's actually some kind of, I'm gonna call it N, like a normal force. It's not normal in the fact that it's like normal to my point mass, like a normal force of Spider-Man to bad guy. And then if I drew the bad guy, he would have, maybe I would draw the opposite. Like I could split it up into two masses and say one has a force on the other has, because equal opposite, right? If you split it up, there's one force one way, one force the other way. But if I add the two together, total weight on that tension is mg plus mbgg, bgg. Cool. And then we had some other people that are like, well, have we considered the aerodynamics of Spider-Man? Like, what is his coefficient of drag? What's his apparent like coefficient of drag times area? I'm like, nice, yeah. Do you ride bikes if you added drag? Or motorcycles? Or airplanes, anybody? Did you add drag because you're every day worried about drag, or just you wanted to cover all your bases? I'm a bike nerd, so I like thinking about drag in my cross-sectional area. No response. Nerd. Yeah, I am a nerd. I like it. So we could add drag. What does that look like if you add drag? So I'm gonna take the bad guy and join him back into Spider-Man. Just make him one big lumped mass, because there was nothing wrong with it. Where does drag go? What does that look like? What is force of drag? I mean, we have like some lines of where Spider-Man's going. Yeah.
It could be like in a surrounding, like the
Opposite.
diagram. Or,
Surrounding.
Or like the opposite of its general direction.
Yeah, so with free body diagram, the main thing that we're trying to do is like, where is this force applied and which direction is it pointing? So if we say like, okay, there's a cloud of drag around this thing, then it's like, well, is that part of the equation or not? Like we're trying to add vectors. So I like the idea of saying like, okay, it looks like Spider-Man has momentum going this way, right? So that means that our drag would be going, I don't know, force of drag that way. And I always call it like FD, because that one's like, so, and the reason I'm kind of going through this with you is like there's certain ways that the problems get approached over and over. So I'll show you my methods that it's not that you'll see my method every single time, but it's something that's at least consistent. So if you're always following the same kind of process, you'll have a consistent process. If you go to a textbook, maybe you'll have like the negative of what I was doing, but something like that. All right. So then the last thing that people were trying to do was figure out Spider-Man's moving. How do I draw that moving force? That was the thing that I saw people like trying to say, like, he's swinging through the city. He's not a static bridge just holding. He's not just like a static swing set. This is like Spider-Man in motion. So how do I draw? So I saw some stuff that was kind of like F, like A or M. I don't know. Like there were different labels for it, but people were kind of saying like that away. Like there's the MV, right? Yeah. You don't draw it? Okay. Don't show it? Yeah. It's not, yeah, so it's not like an applied force, right? So, and that's a great way to think about it. It's like a free body diagram is only the forces applied. So I'm not going to draw motion in my free body diagram. And sorry, another similar thought? Or you feel, or were you gonna like throw something else out there? Like, draw it straight backwards. Momentum, okay. How, yeah, is momentum a force? Can we draw momentum like as a vector of force? Kind of. What's our second law? F is ma, and so F is a change in momentum. So if we know like momentum and how it's changing, then if we're drawing like MA on our diagram, really what we're saying is like F minus MA is 0. So we would add up all the vectors equal to 0. And there's only one person who ever did that. That was L'Hopital. L'Hopital? I think it was L'Hopital. Everybody else says F equals MA, and they say the forces equal motion, changes in motion. But if you want to be like L'Hopital, you can draw negative MA terms on your free body diagram and really confuse everybody. All right, so, and this is totally fine for a free body diagram. If you added extra forces, if you didn't add drag or you added those normal forces, totally fine. All depends on what you're trying to do. This is the new thing that we're doing now. We're saying the free body diagram is equal to MA. MA is a vector, right? We can split that vector up into different terms. We could say that there's an X and a Y component. We could say that there's only a rotational component. We could say there's radial and transverse component. Like we can choose any coordinate system we want. So I could just say, I don't know what they are yet, but I know there's an MAX, I know there's a MAY. And I'm using fancy dots. Have you seen those before? The dots over the, no? All right, so here's the, so the dots are derivatives. It just saves you writing like ddt over and over. And a dot is always like a time derivative. is it always? I'm trying to think of a counter example, but for the most part, if you see like textbooks or written papers or anything, if you see a dot over an item, 9 times out of 10, it means that it's a derivative with respect to time. There are also, have you seen primes? What were the primes? Like a y prime, y double prime. What was that? Yeah, usually, so a lot of time, and again, 9 times out of 10, this is dy dx. Like, what is the derivative over space? Dots are almost always derivative over time. And that one's kind of an aside. But. All right, last time we talked about like free will, like is it even there? How does that relate at all to like drawing free body diagrams of Spider-Man? Like, is it connected? Is there a connection there? Or have I completely lost my mind? I know I've partially lost my mind, like I'm definitely going crazy, but have I lost all sense of reality? Is there a connection here? Yeah.
Do you have to like add a variable or a factor for chaos?
For chaos, yeah, or like, so chaos is like a specific field. I mean, so you could just use chaos in the colloquial term, or like kind of the normal term of just like, shit's going crazy, like it's chaos. But there's also chaos, the field of like, things are crazy because small changes in initial conditions lead to large changes in the final outcomes, which is a lot more boring, but that one's like the official sort of like academic chaos theory, is that dinosaurs will break loose because of small changes in initial conditions, not because like just shit's crazy. So there's chaos. The other thing is like we can do these kind of models and we can build this kind of stuff, but whether or not you believe free will exists or not, or you think it's predictable, you're not factoring that into this model. Like, so you could add a variable of saying like, this lumped mass is true, but it's not factoring in the fact that the bad guy is fighting with Spider-Man, and that is a very unpredictable thing, so maybe we need like random forces added to that or something. But that's why I bring it up. Like, however you kind of fold this cause and effect world into your problem solving process, there's a lot of things that we're not modeling that are very important for our models. So maybe those come into effect in like random, like actual random variables where we know there's forces applied, but we don't know what they are. But that's why I bring it up, and that's why I'm bringing it up again. Okay, Newton's second law. We did this already, so let's just write it down. F equals ma. So now I have my quiz number 2. There's like the main submission. It didn't take, I mean, it took a lot of discussion because I talk a lot. I'm a professor, I can do that. You can do that too. You can train, go to school for a little longer, pick a research topic that no one else in the world would ever do except for you, and then you can stand up here just like me. Okay, so I have quiz 0 done. So the submission would be like this PDF, like print that to PDF, put it up into Husky CT. The other thing I ask for every quiz submission is like a 10 to 30 second, it can be audio or it could be video, of just a reflection on this assignment, of whether did you do it, everything made sense, or are there muddy points that you weren't sure about, like something along those lines. So I'll give you my like 30-second kind of Cooper video. We'll go like a 3, 2, 1, then I'll pretend like I'm submitting my video. Ready? Okay, so 3, 2, 1, and scene. Hi, I'm Ryan Cooper. I just did quiz number 0. I was pretty sure about this one. I've done a lot of free body diagrams, and I wanted to add a kinetic diagram, even though we haven't covered it in class. But I added tension, drag, and then I lumped the two forces together. That one I wasn't sure about because I don't know how the bad guy is actually being held by Spider-Man, but that's my submission. And then F equals ma, I just wrote it as the standard equation. C, done. So that's kind of like the 30-second clip that's expected. Sound good? And each quiz like something like that, of like list what you just like a big picture. What did you do? What did you add? Was there anything you weren't sure about? And then that's it. Yeah. Homework you can just submit like a PDF, and yeah, because we'll do the homework mostly together in class. But I'm a big fan of like reflection as a part of the learning process. So this is really a chance for you to think about, because the quizzes are meant for you to build them, like think about what was important. So we build them together. Then the next part is do it, like actually practice, like do it. And then the last part is, did I really understand it? Like what was I really sure about versus like what's new or kind of unfamiliar to me. And you don't get graded on, like if you said like I was totally guessing, you're not going to be like penalized because like, well, this force was a guess. You're still graded based on like how you approach, like your problem solving approach. Other questions about quizzes, homework so far? Now I think we're like almost into it.
So that free body diagram, there's the correct answer.
The correct answer? No. This we didn't account for the force of drag. Maybe this is actually like somewhere down here. Or I could say since I drew like motion as an AX and an AY, I could have two components of force of drag. I could have FDX and I could have FDY. Like if I'm moving up, drag is down. If I'm moving if I'm moving right, drag is left. And then if everything's opposite, then drag is the opposite of those. I could have, like we were saying before, I could delete that thing here and say there's actually some kind of normal force from like Spider-Man to bad guy. Could I add friction? Maybe. Probably not, right? At least like there's no, we don't have a lot, we have like a quick snapshot of something moving. So like maybe we could say instead of normal force, there's friction of like Spider-Man trying to hold the bad guy. So if they're moving too fast, he'll slip out of his hands or something. But Spider-Man has a pretty high, it's high enough that it can hold his own body weight, right? Like he can climb straight up a wall with no normal force at all on the wall, so we don't have to worry about friction there. Yeah, so there's lots of different ways we can draw, and we're going to keep practicing free body diagrams. It's like meat and potatoes of this course. So is it the right answer? No, it's not the right answer. It is not incorrect, but it's not the right answer. I know engineers don't like that. They're like, is it 2 or is it 3? I need to write down the correct number. It's like, no, we're trying to build models here. So it depends on what the question was. If the question is how much tension is there in the web, then the drag, the normal force of the bad guy, like none of that matters. All we need is total weight and tension. Like get rid of everything and just have those two forces, and then the MA will figure out from there. Cool. Anything else? Let's add a new page. All right, so now we got clean slate. Oh. And then the next thing coming up is like next week by Thursday. I didn't want to jump into like running Jupyter Python like right now because it's a whole thing of like make an account, log into NanoHub, get it up and running. So I thought we could take a look at like module 1, even though, and again, like I don't expect you to have started the readings or anything, but I thought this would be a good place to like start practicing like normal class stuff. Does that make sense? Like jump into homework 1, look at problem 1, and go from there. And then on Monday, we'll try out Jupyter and actually run through homework 0. Sound good? Yeah. Oh yeah, we don't. All right, so Wednesday. Sorry, Wednesday is what I meant. Yeah. Take time, enjoy the long weekend. I just forgot that this is Monday, Wednesday, Friday, so we wouldn't make them. Thank you. So Wednesday, we'll get back to Python. Sound like a plan? Now's the time to be like, no, you're crazy. We need Python now, but we'll get there. All right, so homework 1, do problem 1.1. What the heck is this thing talking about? We are looking at, we can go to reference material, and in here, there's a link to chapter 1, 2, and 9. So these are the things that, not all of chapter 9 is like important for this first module, but at least that like first like rigid body falling example, just to know like what the difference between a point mass and a rigid body is. So we'll open up chapter 1. Cool, that loaded quick. And I'm scrolling all the way down to this problem. I want to get screen area. Oh, there we go. Okay, cool. So the question is, we have frame I and point P. What are the coordinates of point P in frame I? Does that question make sense? What is it? Think so? Yeah. So we're trying to find, we have measurements that describe where P is. How do we like say this is where it is, like in our chosen reference frame, where this is. That's my frame I. That coordinate system here. So take a second and like, how would you write what that coordinate is, like where that point is? Can you see the numbers?
That makes me one of those. It's one of those.
Oh, figuring out.
Okay, I was like, you guys are going way too hard right now. I don't want to beat this level into like so quickly. I don't want to be stupid. I would just use animals. Two is excessive. I practiced it yesterday and I was like, I could not imagine doing this with any less than 15 if I did this 16, what's the difference?
The worst thing is that I'm taking up more space because I'm not in the right place.
I feel like I never buy a second book.
This is one question.
I just throw it on the page.
Question one. Someone with so much more life, I don't know. No, we did solo work because I did that.
They're gonna spoil it. So it's gonna take the whole game and spoil it.
So mostly I saw like this kind of vector format of like, let me put the coordinates in this parentheses like this. So how far along our x-axis do we need to move? I know that's the one that you have to add two things together, but 6.98, like that. And then how far did we move along y-axis? Yep. 3.64, and then z. 1.92. Did anyone write the vector in a different form? Everyone uses parentheses. Is that from multivariable calculus? Did you use parentheses like that? Okay. Can I show you a different way of keeping track of vectors? Because, so like let's say we just like switch these and call this one EY, or wait, what do we want to do? We'll call this one EX, this one EY, this one EZ. Is it still the same vector? All I did was just like rotate. What? I gotta switch all the coordinates, right? Yeah, so so whatever X, Y, Z, however I switch those, I need to switch whatever's inside there. Did I change the vector? Like the actual vector? I see some head shakes, no. Why not? Why didn't the vector change? Still the same, yeah, still the same magnitude, but you can have vectors that are different with the same magnitude, right? So it's still the same magnitude. Yeah. And the direction did not change. I changed how I'm looking at it, but it did not change the actual vector. So this is like, and we'll start using like this notation a lot of like, this is position P, like this is P, and really the fancy way to do it is P/O, P with respect to origin. That vector, no matter what coordinate system I use, it's always the same vector. So the little numbers that are inside the vector might change, but it's always got to describe the same vector. So I'll show you one way of having like a consistent definition for vectors. There's multiple ways. Like one way for this one, you could, like every time you have a parentheses, like say what parentheses that is, like it's in reference frame I, something like that. And that's one way to keep track. Another way is, I'm going to zoom out so I can keep track. I take each magnitude multiplied by each direction, and I add them all up. And now, if I have a new EZ component, like it's pointing in a different direction, I can call it like EZ1. And maybe there is like maybe I did have to travel along EZ1 for a little bit, but I have like magnitudes and directions all just added up together that way. So it's always clear how to get there. Follow this line for this amount of time, follow that line for this amount of time, or space, whatever, space. This is my kind of preferred like vector format, especially for dynamics where things quickly get complicated and confusing. I like this one. It's the same vector though. Like you're just describing it a different way. But give it a shot, see how you like it. Are we out? 12:20. Yeah, we only have 2 minutes, right? 12:20 till 1:10. Yeah.
To use the I-hat instead of the E.
Yeah, like I could call EX I hat. Have you seen that format before? IJK? Oh, all right. Yeah. All right, so let's do that because you've seen it. I, J, and K. So it's exactly the same, right? We're just describing a vector with 3 steps along 3 different directions. And no matter how we go along each one, we can add one before the other. It doesn't matter. Cool. Have a great weekend. And I'll see you on Wednesday, not Monday. I won't be here Monday. Neither should you.